Welcome to this presentation titled The Inception and Evolution of Physical Models for Cable Net Structures, 1964 to 68, Adapting the German Pavilion Prototype into the Institute for Lightweight Structures. My name is R.Whitehead. I'm an Associate Professor of Architecture and an Associate Dean at the College of Design at Iowa State University. This particular presentation was made possible by the support research from the ISU CEAH grant. The primary sources for this are the Frei archives at Karlsruhe, Germany, and of course the library at the Institute for Lightweight Structures in Stuttgart. This was presented at the Construction History Society of America number 8 conference in June of 2023. In 1965, the design competition for the German Pavilion for the 1967 Montreal Expo was won by Rolf, Gutbrod, and Frei. Their entry featured a convincing model of a lyrically composed multi-peak membrane roof hung from Mast, and it was articulated with teardrop loop connections floating above the grounds. As it was proposed, it would be the largest pre-stressed cable net structure in the world. Because the experimental structure of the form, one was derived exclusively from formative principles of tension and the unprecedented challenge of designing and constructing this within 18 months. Otto recommended that this newly established Institute for Lightweight Structures in Stuttgart begin working on the design, analysis, and construction process. So my paper is going to talk about how the different types of models that they used evolved throughout the process, going from the first types of models to the more measurement models to the final prototyping. The overall project data of this is basic data worth looking at other more in-depth sources about this. But of course, it was for the German Pavilion for the 1967 Montreal Expo. It was intended to be the world's largest cable net structure at 8,000 square meters. The project team consisted of Rolf Gutbrod and Frei Otto. Frei Otto ran two different research institutions here, one in Berlin and then one in Stuttgart, and those are also listed as the EL and the IL. Both of those were researching lightweight structures. Their engineering partner was Fritz Leonhardt, and then the cables and membranes were done by Strohmeyer and Company, which I'll talk about in a minute. There's also a process of photogrammetry in which they tried to photograph the models done by Klaus Linkwitz. Purpose of this slide is to talk first about the overall complexity of the project, but then to point out with the asterisks there that there is a large amount of teams that were centered in and around Stuttgart. There's quite a few interesting stories about how the competition team approached Otto and Gutbrod and kind of pushed them together, and how they were selected in only the second round of the competition and basically invited to apply. The perspective I'm taking with this presentation is how I normally look at the construction history view, which is sort of a warts and all view of projects. I think projects are more interesting when we step a little bit back from just saying, hey, everything's great, to actually look at what was difficult about them, especially with experimental structures, really to find out what it was that drove the process and how in this process of experimenting something was learned. And for something to have learned, usually there's some sort of failure. So in this one in particular, we're going to talk about the process and the product of it, and we're going to find that it was both remarkable and flawed. And it's not just my opinion saying that. You can see Otto's quote here from 1975, where he talks about it was screwed together very roughly in only a few days. I mean, frankly, it was 5 weeks to put the whole thing together. And he calls it an unoptimized pattern with many tolerances and faults. And I think that this is a really interesting way to begin thinking about the project, is also through Otto's idea of it, is it was really remarkable. There were new forms and a, quote, peaceable architecture that he talks about, right? Fantastic, but there's also these limits that come with it of this process that was somewhat flawed. The perspective for all of this, every single thing that I'm going to talk about from here on out, is dictated by this tremendously aggressive project schedule. I want to start back here in 63. The expo invited attendees. Germany took about 9 months to decide that they wanted to join this. They then took about a year to figure out how to run the competition. They then ran 2 stages of the design. So Gutbrod and Otto were selected at this point. And I want you to look in particular at the orange and yellows and reds in here of the compressed design timeline. within this very short timeline, they had to go from schematic design to something that could be built. As of this date, they were building foundations and masts and net. And of course, they had to install exhibits and everything like that at this as well. So all this was just incredibly compressed. Up here on the top, you can see that I'm starting to talk a little bit about what some of these models would be as we go. As we project a little bit further out, you can see that eventually they would be building the full-scale relocation for the Institute of Lightweight Structures, and then occupying it a year later. And then, of course, the Munich 72 project began not long after that. This is sort of inextricably linked, some of these particular models and their process, with the Munich project. But we need to start from this idea, why tents? And then how? How could such, in other words, a uniquely complex building be designed in such a short amount of time? If you had such a compressed timeline, why would you say, let's do something that's never been done before, right? There's no conventional methods to design, analyze, or document structures like those tents. Otto, as you hopefully know from other perspective and research on this, had been doing tents for many, many years at this time. So a worldwide expert at it, but there was no tent that was this large. So to answer the question about why tents, I think we have to first start with the sort of perspective of this, which is what the competition called for was the idea of finding a new master builder of 67. There was really a tradition in German pavilions at World's Fair, including Mies van der Rohe's at the Barcelona Pavilion, of really showing how Germany's view about architecture was something that was interesting in perspective. So the competition called for bold proposals to represent an open and democratic society through its external shape and design. What this means, how it was translated specifically into tents, is a lightweightness, right? The progressiveness of this couldn't be something big and heavy and in any way referencing any of the sort of fascist Third Reich architecture, right? So instead it has to go to something that is lightweight and transportable and, incredibly unique. It also is a really interesting kind of critique against a 1950s conservatism ideas in the German Federal Republic, particularly in architecture, that this really takes them beyond a pretty conservative perspective. So that's one reason of why tents, and particularly why Gutbrod and Otto's competition won. But also in the competition, the evaluation criteria said that the schemes had to be, quote, prefabricated structural components with easy transportation and assembly. Well, okay, this is something that could easily come along with tents as well. One of the main construction methodologies of tents that makes them unique to other things is, of course, their transportability. All the mesh net that you see is able to be rolled up. There's very few masts. There's very few foundations. It's huge and it covers a very large amount of area, but compared to traditional building construction, look at the ones behind it in the photo, right? Compared to some of those, this absolutely is designed to be something that could be built relatively quickly. The other part about how tents or why tents is that there has to be an effective morphology and an efficiency of the design. For the competition, Otto suggested that, and once he and Gutbrod were sort of shortlisted for this, they had a very short amount of time to put together their presentation. So Otto suggested they, quote, take something from off the shelf. By that he meant, let's take something that we've already been working on. Let's see if we can just repurpose that. Therefore, that we have such a short amount of time to be able to develop the design, we should have something in place first. So what they used is this model that Larry Medlin, and Larry Medlin was a student that Frei met at Washington University in St. Louis back nearly 10 years before this. Larry Medlin came to Germany and was working with Otto, and he was one of Otto's, I think he was a partner in Otto's firm, one of the very few people in Berlin with him. And Larry Medlin made this eye model, this eye loop model that we see here. The idea behind this eye loop model was, unlike other tents that had a mast that came up and had a big, huge, heavy cap on top, this one actually spread out all of the stresses around the eye. You can see that Otto has also been sketching about these eye loops as well, and these series of sketches from one of his notebooks right around, I want to say 60-61. In this, he calls this thing loaves. So you can see the form of what looks like sort of bread loaves that are looped around if there's multiple eyelets. And here you can see two different thoughts that he has about how those eye loops might be. And then through physical modeling, of course, we're able to find it. So then back to this particular model here on the right, on the left, this thing has a very, very regular, really interesting scheme. They have high and they have low. So why does this make sense? Why did I call this an effective morphology of design? Because in order to have tents work efficiently, they have to be stiff. Okay? In order to get stiffness, you need double curvature. You could have really high mass and have really frequent mass, and then have a lot of frequent tie downs, and you could get double curvature that way. But the thing is that really disrupts a lot of the interior space, and it puts a lot of stress on the membrane. Membranes back then absolutely had limits as to how far they could stretch. So instead, the brilliant idea, go high, low, high, low. And in that, you then get more double curvature because the membrane itself only has to span a certain distance, and then it quickly curves the other way, right? So a high and a low. And both of them then are able to ease the stresses, both the high and low supports, ease the stresses on the membrane because they both have these eye loops. It's a really effective way of lessening the amount of shear that's on the membrane, getting double curvature in order to keep the whole system stiff. And obviously this is a stunning interior space. Why tents? Otto also contended that they were easier to design. First thing I want to point out here is that they did complete this model. It's a 1:200 competition model, mostly Larry Medlin working with the partner at Gutbrod's office. They completed this thing right under the deadline, probably an hour before it was actually due. Otto insisted that tents had forms that were to be found and not designed. What he meant was like, it'd be really almost impossible to sketch this accurately. So then in his view, making this model of it set the design forward. This is what it was going to be. Why? Because the form of the mesh netting suggested that this is actually the only real way, based on the parameters of the height, based on the parameters of the outward support, and the overall parameters of the plan, that this is essentially what the double curvature of a mesh net would be. It was found. Thus, the design and documentation were inextricably connected. Therefore, in his idea, it could be rapidly made, right? There's no going back. There's no going through a whole bunch of different iterations of what this could be. This would be the design. And so this competition model accurately located all those parameters and said, there you go. He used this physical models. He also knew that this question of how would we be able to develop this, he knew that he used physical models for this. He knew that these physical models, as they got both at a higher scale and more refined than 1:200, could also be tuned. And by tuning these particular models, that would help them build it. So let's see, did he do what he said? Is this thing regular? First thing I wanted to mention here is oftentimes when people see the overall plan of the netting, and here you can see this as a contour plan of what the final proposal is, they think it's pretty wild. And there's 8 masts and there's a lot of kind of up and down to it, and it really seems kind of difficult to comprehend. That's Gutbrod's doing. Otto still wanted to maintain something that was a lot more similar to this first individual model, but Gutbrod thought that they could take these same principles of double curvature and go high and low, but have a more complex perimeter, particularly here, that reached out for the auditorium. But did they still maintain the effective morphology? You bet. High, low, high, low, high, low, up and down with it to be able to get that double curvature. I also wanted to point out there's really a lot of these connecting axial lines that go between here too. So while it may not seem like it when we look at it from up above, it may seem like there's a lot of kind of randomness to it. Once you start to see these connectors, these diagonals and other alignments with it, you see that actually Otto was able to get some of this regularity to it. How else was this able to be done? Well, and I think this is probably the most largest factor, I would say, the most influential factor in the success of this. And it has to do with the fact that Otto had a trusted collaborator who knew how to construct tents, and that was Peter Strohmeyer. Peter Strohmeyer of the company, L. Strohmeyer and Company, out of Constance, Germany. He was one of Otto's earliest collaborators. When Otto was writing his thesis, Das Hängen Dach, in 1950s, he contacted different German tent manufacturers and wanted to know if he could ask them some questions about it, because this was actually a pretty groundbreaking thesis about cable mesh nets and tent roofs. Well, Peter Strohmeyer was the only one who responded, and he invited Otto to come up to their plant with him. So that was then the quote, most productive working weeks of my life. What they would do is they would talk about different tents and different tent geometries, and they would watch how those tents could be constructed. So this competition suggested, of course, that each design team have a partnership with the builder. So it was obvious that Otto would choose Strohmeyer, and Strohmeyer assured Otto that they could do it based on what he had thought he was doing. And he said this type of construction is easily economical to transport and can be used in a wide variety of forms. He told Otto this in a letter. What I wanted to show is that here's this relationship between, Otto making these thesis projects. Strohmeyer then sponsors quite a few of Otto's tent structures and built almost all of Otto's tent structures in the 50s and early 60s. And the type of relationship they had, here's a letter from Strohmeyer to Otto. In it, they were talking about different ideas, and even at the bottom, Strohmeyer is talking about different forms and different stresses of it. So very close relationship that really allowed this thing to happen. It's such an important part of this and the construction of a tent that Otto's sort of most trusted team members, Larry Medlin and Schilling and Burkhardt, were all then stationed at Strohmeyer's factory for a large portion of this competition. How else do you do something like this if you got a tight timetable? Well, you need some cheap labor, right? And I love this quote from Ted Happold, in which he was talking about Frei Otto's work, and he said sort of, I mean, not really with a lot of judgment, that the existence of cheap student labor caused the development of Frei Otto's model testing methods. And it's true. There was 70 plus workers during this time. The average age of them was around 30, and they spent 24,000 hours in here. And people were, as Just Tomlow recounted to me, and this was something that he was there slightly later than this but he knew the experience of working on these models is people would be working night after night, shift after shift. And I wanted to show that they have this sort of super hard work. Then you can see that they're also here kind of really having a blast and having a good time as well. So what you have then, of course, to recap, is you have really good, solid ideas for how a tent could behave the best, right? You have a modeling technique that you knew would be efficient. You have somebody that's able to build the tents that you have imagined, and you have a cheap labor force. So part two, the idea of this physical modeling, how did this actually happen? You can see here that Otto is basically saying, well, there's no way to really calculate it. So we're in the midst of trying to theorize about this and practice. And so they end up doing everything, quote, with our hands. So these physical models, what's so important about these and what's so unique about this, mostly because it's all pre-computation, is that these physical models that they made were meant to communicate the form and the forces of the lightweight structures. There's really only, as like, again, the model form is found. It's not just found, but these things could also be measured. Super important point. Because these deal with tension stresses, you can actually scale up different models and track how much stress it would be in a full-scale model. In other words, if you use materials of a similar elasticity and strength, and you build a 1 to 10 model, and you find that this thing has this particular amount of tension in it, and therefore it elongated this much, you could scale up both the stress and the strain 10 times and be able to predict how a full-scale building would work. So these are not intended just to be pretty models or something to look at. They actually were meant to be able to give them a really decent estimate for how they'd behave. But obviously perfect accuracy for models is impossible, and so problems can scale up too. So we'll look at a couple of these. What surprises some people about this is, if you know anything about Frei Otto, you might have anticipated that the very first model that would happen here would be some sort of bubble model or some sort of abstract model, but it wasn't. So I want to set us at a time frame here. This is 1 month into the design phase of it, 1 month, okay? Otto lays out a super detailed memo that he sends to the design team in Strohmeyer's office, and he lays out their strategy for design build testing to commence immediately. He asked them to build a very large frame, a 5 meter by 5 meter frame, in which they were able to test the key features at this scale. What key features? First, a cable net. He knew that they needed to have something that they thought would be around a 50 centimeter by 50 centimeter cable net grid. They knew this would be a decent scale, not only because it was divisible into quite a few things mathematically, but there's actually a pretty good scale for people to climb. They knew this would be a way in which people would be able to put it up. So they broke that down to 50 centimeter by 50 centimeter. They knew as a cable grid that they had to connect it at these points. So they actually made these prototypes. He cast these out of plaster and sent those to make a mold so that they could then be cast out of metal as well. So Strohmeyer built this thing out of a series of strips, put it in a frame. Then in the frame, they'd be able to test out how they'd be able to tension it, how they'd be able to hang something from below or even hang something from above. The main takeaway from this idea is that the very first model, no other models could actually happen unless they knew these were possible. You have to establish the cable net dimension first, and you have to be able to see whether this type of system also allows you to pull and tune and tweak it. So the next model that they made was at a 1 to 100 model. It's not shown here. The 1 to 100 model, the purpose of that particular model was to establish the key dimensions, as it says here, of the mast height, the mast location at the base, the location of the perimeter supports, okay, and then overall general form of the structure. They did this because they had to be pouring the foundations really soon. So in order to pour the foundations, they'd need to know how tall that mast was, even what angle that mast could be at in order to get this double curvature. So these are your most basic parameters of the whole project. It's not the one shown here because they actually built that one out of the same sort of fabric mesh net that they built the competition model. Well, I want you to look at this competition model and you see how you've got this fabric and this sort of two-way fabric. Well, this two-way fabric is pretty tight mesh net, right? When you put that and subject it to different stresses, it's going to pull and twist in different ways. That fabric would not behave the same way as the cable net. Therefore, it wouldn't take on the same form, and therefore, you couldn't measure from it. So because they built this thing out of fabric, they eventually had to ditch it because it wasn't going to give them any more information besides just where those main parameters would be. They built this next one on this gigantic steel base down here because, of course, they wanted to fix points and have them be permanent. So this is what they call a measurement model. And a measurement model is exactly that. This thing is not just representational. This is meant to confirm different dimensions and different tensions, and it's meant to be built so perfectly that you should be able to model any particular point around it. So they built this huge measuring bench. They decided in order to have material that would respond the same way from stress and strain as the cable net, they would use fine spring steel wire as a 12 millimeter thickness, and so elastically it was really similar, okay? They used this model to test for the behavior of this thing under loading. So in that they'd be able to pull the different tension and they'd be able to see what it would be like. This thing was a confirmative model, meant that they actually had to build a series of different tools to go along with it. It wasn't just building the model, but you had to be able to measure it. Just as a quick example, a cable net, when you turn it into an anticlastic form, an anticlastic meaning 1, 2 curves, so a double curvature. There's lots of different degrees of curvature you could get, right, between this one and that one. I want you to look at the difference between how a cable net that starts off as a square might then change from before and after, okay? So that change in the dimension of the net, slight change, okay? One side will be pulled more in tension than the other, but in doing so, that then is the accurate geometry that you need to convey. You need to be able to convey this in plan and section and elevation. You need to be able to measure it so that someone can build it. So here Frei Otto is demonstrating this tool that he'd invented, wherein the plumb bob comes down here level. In that, it's cut as a hole. It points to one of those points in the square, and he's able to make an annotation up here, boop, and pop that down. Lifts up, moves it, gets to the next square, boop, marks that, to the next, and to the next. And then in plan, it's a, quote, perfect plan view of the plan geometry. You then can do this by then taking photographs to the side to also figure out the Z dimension, right? So he's trying to find X, Y, and Z. They also had to invent tools in which they used a standard square, and they could put this on the model and photograph it to see how much each one of the other squares had changed. They had a system in which they could tension it by pulling screws through this. So the main support cables here, the main ones that are coming down and down and down, they needed to really measure that amount of tension. So they would pull it through those screws, and that's tune it, tune it, tune it. They could measure with the protractor how much the angle changed. They could then also, if they wanted to just find the overall geometry, corner to corner, corner to corner, and be able to map it that way. They also invented a tension gauge. So this tension gauge that they had, you could actually apply it to the model. I think if we go back, you might be able to see these tension cables in there. You can see how they're incorporated all throughout there. And what those tension cables do is it's got a little meter on it, and it shows how much tension, because it's secured on the two ends, and another piece that loops around the back. And so if that's pulled in tension, it pulls the meter up. So in that, you could then, again, tune this thing and say, we know how much tension is on this wire versus that one versus that one. So you can measure it on the end, you can measure it in the wire, you can measure the change in the geometry, and of course then they photographed a whole bunch of it, so they had to label all the different parts and pieces so that they could keep track of it when they translated it into design. Yes, it's insane. Can you even imagine the backbreaking work requiring such a high level of accuracy? They tried to incorporate this system called photogrammetry. Klaus Linkwitz was in Stuttgart's Institute for Geodesy. Geodesy is, of course, the measurement and mapping of the Earth or other complex three-dimensional surfaces. So he was trying to figure out a way to add computational accuracy to map the X, Y, and Z coordinates of the model. Decided one of the systems he had used was this photogrammetry system, in which he'd set up cameras all around a room, time those cameras perfectly, and be able to take photos of it, then measure from those photos. This way would then be able to give you a very accurate kind of geometry, again, of the square mesh. They then decided what they would try to do is to see how much it would stress under the amount of weight that was finally added to it. So in this giant frame, they then added weights hanging from cables down below, put this on a board, and they used an inflatable raft down below. They would deflate the raft. First, they would take a picture of it with the raft inflated. They would deflate the raft and then take another picture. So you could take a before and after to actually show how much it strained. I want to make sure I'm super clear here that this was not fully integrated into the design and analysis system of Montreal. Linkwitz was just really trying to figure this out during this phase. They all saw the potential for it. They did their best with it. It was more like helping them confirm other things. But Linkwitz really continued this work and really advanced it much more in the German Pavilion, in the Munich Olympic roof project, and actually turned this into a system of computational modeling. If you're interested in this, I should mention that there's an article in Technology and Design, TAD journal, that I wrote about the building of the Munich Olympic roof stadium. You can find that online. The other model that they did was a wind testing model. This model was based on a contour map. What were they trying to figure out here? Why would they make this thing out of wood? Right? I mean, wouldn't you want to see how much that the membrane would flap or if the membrane would tear? No. They knew that they had to have those other parameters tested another way. Instead, all they were trying to figure out is how much uplift they would have, how much, whether these masts would actually affect the flow of wind around it. And so it was fine if this thing was a solid model. They then drilled a whole bunch of holes in it. If you see every number here, each number corresponds to a hole. That hole corresponds to a tube. And at the bottom of that tube was a series of liquids. And so when they would put it in the wind testing equipment, it would come up and over it, and that negative pressure then would be able to pull up on each one of those tubes. So they could see, depending on the different tests they do, how much wind pressure, how much uplift pressure. They could compare that to their overall design parameters and see whether or not it was fine. All right, what'd they find out? Double curvature was good. It could resist uplift. The masts, luckily, didn't require any special anchoring because at that point the masts were already under construction and the foundations were basically being poured. The main data from this wasn't actually done in time to incorporate anything specific into the final project. All right, now it's more than a cable net. This actually has a membrane to it as well. So how do you know how big the membrane is? How do you actually figure out how to build the membrane? If this model again is accurate, because it's a 1:75, then they were trying to figure out how they could then put a membrane system on it. Now this changes from what we called before is a measuring model to what's now called a pattern model. The pattern model being the pattern, just like you would do for clothes, to make the membrane. They layered paper over the model. Paper can only fold in one direction, right? Because it's paper. So they oriented it in such a way that has a single curvature. So that means they cut it in strips. So they cut it in strips and had to, again, like a dress or something, have these different seams in which this thing would all come together. They then had to hand measure all these pieces that they had put together. They're then hand measuring every part and every piece of this. From that hand measurement, they would go back and they could then draw what looks to be a plan. Okay? Honestly, this is so much trickier than what I just described because they would take general dimensions, verify it with a photogrammetry. They would then project the photogrammetry on a screen, make sure that what they projected on the screen was in fact to a proper scale. Then they would draw by hand on top of what was on the screen. Then from what they drew by hand, they would then convert back to this one particular drawing, which was a 1:200 plan drawing of the patterns. If that sounds crazy and accurate, it was. Imagine that this model at 1:75, even a 1 millimeter error would result in a 3-inch problem at full scale. And of course, especially when we're talking about alignments of these patterns, if you have 3 inches off in one alignment, or you have, let's just say, 0.001 degree angle, that then affects the next one, and the next one, and the next one, and it all compounds as it goes around here. So there's this remarkable nature that this thing got built, and that it got built relatively as accurately as it did. Strohmeyer was convinced that there had to be a limit to each one of the overall membranes because there's stress limits to the membrane, but also they wanted to build in a little bit of flexibility so they could actually make this work. So all the membranes were limited to 400 square feet max. So take a look around. When you look at this and you see all these thin strips, then you see that those thin strips change orientation and change orientation and change and change and change. It's because that's reflecting exactly how they then built it on this model. Next, the patterns in the seams weren't really aligned because it would be impossible for them actually to make this a tight membrane. Okay, so they use these huge seams on the side. And again, maybe if you've ever seen this project, you may not have really noticed those or not really been sure what those were. But they had to have these parts where all these huge things came together. They had to account for that discrepancy, then the imprecision of the model, and they did that with these seams. Okay, so that was the design of it here. What you're going to see is I'm not going to talk about the actual construction of the German Pavilion itself, but I am going to talk about the actual prototype that they made of this that was also a full scale. So they called it construction of the tent. We've now had a competition model. We've had a measurement model that used the wrong material. We used a measurement model that used the actual steel material. We've used a pattern model. We've had photogrammetry. All of this helps, but they haven't actually put this together in any particular sequence. So Strohmeyer and Otto knew that they had to practice the sequencing of building this. They have to be able to build this thing really, really quickly, right? I mean, in order to make this work, they only had weeks worth of time in order to actually construct the full thing. So from the onset, actually Otto and Strohmeyer proposed, and we can see this here, at the very onset of the design, a full-scale prototype was planned. They then worked for the funding of it and realized right when they were done with the design idea that they should try to build this. So foundations are in. They're getting ready to have Strohmeyer manufacture all the mesh, tents, and everything else there. So this is their last big thing that they had to do in order to make sure that all those details were going to work. The other thing I want to mention here is this also was a kind of go or no-go demonstration. Could this thing actually work or not? Remember, there was no cable net structure that was this big anywhere in the world. So all the things that they were trying to figure out, the mast, the perimeter, the net, the membrane, all of this had to be figured out. It was full-scale details, but done at only 1/17th scale proportion, meaning that they didn't want to build a 150-foot tall mast. So the scale of the mast is relatively modest in this, like 40 plus feet. It only covered about 650 square meters. You can see when it was built, the idea here was they'd be able to resolve all their problems that they found, but to have it in a pretty tight amount of area. Okay, big asterisk though. When Otto talks about this, he actually talks about this in a different way, especially in retrospect. Because the one thing I think I want you to recognize about this particular design is how it's all pretty complete. It's all pretty symmetrical. One mast, perimeter, all the way around. This is super easy compared to anything else. There's no low part. It's just a tall mast with one eyelet and then perimeter support. So it turns out that Otto, of course, had been working at Stuttgart since 1964. Right? We're now at December of 65. He was actually working off campus in a building that he didn't love. That wasn't a modern building. It wasn't an interesting building. It really wasn't contributing at all to the overall research goals of his institute. So what Otto calls here is his, quote, big trick. We needed a better dwelling. In a hurry, we staged our big trick. We made the federal government of Germany donate us the net construction of the experimental building. So I contend that, of course, this was the plan all along was, and why not? They needed to be able to test these details at full scale anyway, right? So if you're going to build it at full scale, why not figure out a thing that you could build that actually would be the perfect size to house a research institute? And frankly, what better research institute to have than one in which was a full-scale prototype of what was going to be Otto's, career-defining project? So bubble models. We've not talked about this before because frankly, bubble models are fascinating. There's an entire lecture about this, about how they're generative, self-forming, minimal surface tension. They're super easy to create, believe it or not. It's just really hard to abstract information out of them. The reason I bring this up is because here's a bubble model that Larry Medlin did of what would be the tent here, the IL tent. You could then take that and you could add contours to it and you could find out, and this is sort of a photo projected contour on here that you could then take a photograph and measure. You can see then from the side in their machine that they would be able to measure this. So again, they could plot the Z coordinates on it. This work of trying to actually measure a detailed model, this was done in thesis projects that were well after the tent was constructed. Okay, this thesis project in particular was 68 to 69. And then the bubble work continued. It started a long time before this as well, continued a long time after. My point is this. This is a model of, an aspect of the German Pavilion, but this was really done as a way of trying to enhance the design of the tent itself. This gets really interesting because it's a relatively unknown part of this particular project of them actually building the prototype of it. So they decided they would follow the same sequencing as the scale model. They post-tensioned the perimeter, fastened the cable net, and it performed basically as they had designed it. So they found out that when they actually built it, that the mast and the mast details, the connection down here, the way they were able to tilt it up, the fact that the top part of the mast had a small way that they could be able to extend it up and down to be able to pre-tension it, the system in which they were able to hang the primary support cables from the eye loop, the idea of being able to stabilize that with the guy wires on all the sides. Then, of course, how they're able to connect these different cable nets together, how they're able to then pull it up. What I'm showing you here is, of course, things that were in the prototype, and then things that became evident in the final construction of the pavilion at Montreal. Overall, the cable net and the mast all performed as designed. There was some problems that came up, and so it's like a really good idea that they did this. One of the foundations, as they were pulling this thing together and tensioning it, actually broke. You can see here how that is now loose, how it popped out from here. Okay, so they did this right before one of their major demonstrations, and so they found out that there was a sequencing issue with that. The connections were a little bit difficult with it. They also found out that it's because some of the foundation dimensions varied, in fact, quite a bit, as you can see here. The other thing that they had mentioned that Medlin and Burkhardt mentioned in their confidential report about this was that some of these edge supports were slightly different dimensions. I mean, 10 centimeters too short. Think about how tuned this model has to be. If this is at all any shorter than the one next to it or at a different angle, then trying to have a uniform set of tension all the way around isn't going to work, right? So they had to be able to find the perfect sort of uniform dimension around there. They then used this as a way of trying to understand how they would hang the membranes from this. And so you can see that, again, you've got the mast that's hanging all the net and the net that's hanging the membrane. Here's a part of the design for the Montreal Pavilion that maybe some people don't understand, is that the membrane itself was not structural, was not doing all the work. The membrane isn't even on top of the cable net. The membrane hangs below it. So the cable net itself is what's holding up the main structure, and then the cable net has to support the membrane. The membrane then has this gap in between. So they're able to then use different hangers, pull the hangers up, essentially use the mast itself as almost a crane that's being able to lift this up into place. What they found out, it was a little bit difficult to sequence it and to fit, but overall that strategy worked. So you can see here then the prototype, and here they are at the Montreal Pavilion, and you can see the membrane down here getting ready to be pulled into place. This to me is the most interesting detail that they came up with for how then they would be able to pull this thing into place. I'm going to go forward and then come back. They used a set of prototypes here in which they had a bar that spanned between the main cables. This bar then had a vertical piece to it that was then connected to what looks like a frisbee underneath. This frisbee then is on the underside of the membrane, and it allows the stresses to be spread around the surface of that frisbee, so you're not holding that membrane up through one specific point. Okay, so how does this frisbee then connect to this bar, and how can they make that so it would be tuned? So the first thing they found out was they needed to start from the bottom and pull their way up. So they tune it each and every time. They hang it in a general position. How do they tune it? Here's sort of the brilliance of this full-scale detail. This bar could slide side to side in between. You could also fix one end and it could rotate. You can see how just the rotation of it changes the tension on that particular wire. With this bracket on top of it, you could then slide it this way or that way. It's pinned here, which means that then that also can rotate. So if this point stays the same and you pull it over this way, then it rotates in that direction. Or it sort of slides up and down this way. Then you can tune it one more way. It's a turnbuckle on both ends. So you could tighten or loosen it, which means that you could pull it up or pull it down. Why the lengthy discussion about this? Because you then have a square grid that you can adjust the tension to this grid, but then the bar, you can move it on its X or Y or rotate or move the X or pivot it so that the membrane itself could actually be tuned so that membrane stays in tension. And it also means it can work at a slightly different geometry than the cable net if you need it to be. You can't see any sags. You really can't see sags in this membrane. You have to be able to pull that tight, okay? But the membrane is going to behave differently than the cable net. So in order to allow it to behave slightly differently, both from a material and a structural perspective, you might actually pull it in different ways. It might not be a perfectly uniform gap between the cable net mesh net and the membrane itself, okay? Now, in general, what you're going to see is that there are regularly spaced frisbees, for lack of a better term, right? And that where those frisbees are located is not actually that well coordinated with where these other seams are, again, because of the way the modeling happened. I also want to get you up close to be able to show you one of these splices. These splices just have a whole series of eyelets there. You can see that the membrane itself is doubled and tripled layered because of all the stress that's going to happen on those ends. You take one end and you pull it, one end and you pull it, so that way you're sort of fixing these two ends together, holding those back to the main support cable. And then if you wanted to try to make sure that these stay tight, you're sort of pull, pull, pull like shoelaces in between. They did uncover another problem even after they had had the foundation fixed. It was that the eye loop itself, the geometry of the eye loop after they had tuned it, was different than what they had anticipated. So you can see this thing that they built as sort of a lower budget scheme for what they ended up with, which is just essentially a clear membrane for this eye loop. You can see it's being pulled in place and eventually pulled up here. What they had was it was slightly too long and slightly too narrow, and so that they couldn't actually get the right amount of tension around here. So they had to be able to adjust back to these main cables and the main cables around there. Interestingly, this is what the bubble should have done right, was be able to get this geometry exactly right. But again, because the bubble geometry isn't exactly something you can hold a scale up to get the right dimensions, it won't really work. So this is really well done in the field, and really important that they did this in the field so that they could learn lessons about how to tension this correctly to get the right eyelet geometry. One of the main conclusions of this whole series of ways of talking about the model is actually what came out of this was a parametric algorithm for optimizing the model. You're looking at something that I translated from a series of hand sketches from a graduate student who worked at the Institute for Lightweight Structures during the Montreal project named Mick Eekhout. What he ended up doing was writing out a set of different ways in which you would have a task to be put forward. You can see he's talking about liquid film models, photometric measure of the film model, construct the Tully model. Tully is the fabric that we were talking about, structural modifications, etc. So this really maps out the process that I had just shown. At each and every point, then you have this red sort of diamond shape. This is sort of a go or no go. Does it work? And then if it works, you move on to the next one. And there's several different parametric choices here. This is in the Technology and Design journal article. The reason I bring this up, because this is a super important way of thinking about how we make sense of all the models that we just saw. It wasn't just about making models visually. It wasn't just simply about how we could measure them or how accurately we can measure them. This became then an actual algorithm for decision making and optimization for the models that turned into both a physical and digital modeling process for the Olympic roof in Munich. These basics were established by Mick Eekhout and the rest of the model making team during the Montreal process. So the sort of appendix to this is like, okay, they built this full-scale prototype. The German Pavilion is constructed, huge success. And after the completion of it, Otto then became renowned worldwide, and he wanted to make sure that he could leverage this. So as he had mentioned before, when he talked about the, quote, big trick, they needed a new home at the campus. And so he knew tents were adaptable and redeployable. And so he knew that that would be a perfect, this lightweight structure would be a perfect way of housing his research institute. So he moved the prototype. There's a lot to be said about Otto as an educator and his views about what this research needed to be. One of my favorite, simplest ways of talking about it is how he did. We called it the Zbinozentrum. In other words, like the center for crazy people, because he knew that like you needed to have this kind of, it also means like creative crazy, right? This center for sort of creative energy that was all together. This is where it also gets interesting, is because then they took this structure that was, I should mention, it was about 2 kilometers away where they had first constructed it. They knew that was only a short-term solution. So they deconstructed it, which also proved a major point for Otto, ideologically, that tents could be deployed, redeployed, and adapted. So with additional funding, they had it taken apart. They moved it to their new location on the Stuttgart campus. Okay, so here it is, wrapped up, pulled with the crane. They get it to the new site, sort of stretch all the cable mesh out. They located it there. They needed to give it time to retention. Then they actually worked on different prototypes in which they were going to add a wood cladding system to it. This can't be a temporary net. This actually needed to be a place that was insulated and it was permanent. So Otto goes back to a detail that he knew of from Fred Severid. This would be like the equivalent of the Ingles hockey rink between Severid and Aero Saarinen, in which they had a cable mesh net with then this wood slat system. So they have this wood slat system. Okay, you can see the wood slat system there. They have these primary wood slats that would run up and around. Then they'd run secondary wood in between. They then could add insulation on top of that. And then they, of course, needed to weigh this down and to kind of recalibrate all of it before. Because the geometry of this tent as it was before was basically just meant to hold the membrane. So it's holding a much different type of a load, which meant that to keep the overall double curve geometry, they had to reaccount for the amount of stresses in it. Now, the added weight of what this wood and the insulation and the shingles would add, to me, it's really sort of interesting, not a coincidence, that the cable net itself and the primary cables of this tent were actually initially sized to be able to hold all this extra weight. It's almost like in advance they knew that this thing had to be holding more than just the membrane. And I think, again, Otto has tipped his hand on that as well. You can see some of the other details now as they're permanent here. These are the foundations that we had looked at with the prototype before, how they're tilting outward. Here's an image from Larry Medlin's slide collection that shows how then they had to be able to incorporate a window system and a sort of a perimeter around it. One of the difficult things, of course, with net construction is that how difficult it is to actually get enclosure around it. And so they had this really interesting system of a curved foundation and then the glass that came in between. Here's a view of it from 2022. You can see that the main mast is coming all the way up. You can see how the light comes in through. You can see these primary wood slats. See the double mesh cable net in here. All the sort of things that Otto was trying to get out of this double curvature and this combination of light and materiality. It's still adaptable. It's still being used. They're still doing incredibly interesting research work at that. So overall, then you can see that the inception and evolution of the physical models for these cable net structures really went from things of bubble structures and when and where they used it, to the measurement models, to the pattern models, to the full-scale prototypes, and how all of those then evolved themselves. Thanks for listening. Appreciate it.